All right. Nothing like a rousing introduction, right? Okay. Let's go ahead and move on. We're in chapter 20. We're going to be talking about how chemicals react. Okay. A couple things. First of all, let's just look at this right here. All right. Let's just look up close here. We talk a little bit about reactions. I'm not going to spend a lot of time on this because it's on the video, but we'll do a little bit. Anytime chemicals react, okay, we have two types of chemicals. We have the chemicals that we start out with. Say we had sodium that we dropped in water the other day, plus H2O, which is water, okay? And those are the chemicals that we start out with, and those are the reactants, okay? And guess what they do? They react with each other. That's why they're called reactants, okay? So they're the reactants, all right? We put this little arrow here to show this is where the reaction happens. Okay, something happens, and then what do we have afterwards? Leads to, reacts with, we say sodium plus water reacts to form or reacts to produce two things. We said the sodium, Na, joins up with the OH, one of the oxygen and one of the hydrogens to make, name it, that's right, sodium hydroxide, okay, plus hydrogen gas. Okay, now hydrogen gas and oxygen and nitrogen and a few other gases like that are we'll call it diatomic, which means there's always two of them. They have a buddy system. So if there's two hydrogen gases, that represents the gas. Now, this is what is a base because it has the OH group. We'll talk about that, and acids and bases coming up. But it is what turns this up purple. Okay, and then the gas, which you're giving off as hydrogen, you couldn't see that, but it's what caught on fire and blew up. Okay, so anyhow, so these are produced, so these are called the products, all right, which is what you end up with after the reaction. Now, occasionally, if something has to happen in between here, we might put something like heat or light or some other energy that sets it off, okay? If we were talking about burning paper, we might put heat or specifically a match. But anyhow, you get the idea. Some kind of heat has to be there in order to make it happen, okay? Or, as we'll talk about today, we might put an enzyme has to be here, or a catalyst has to be here. Okay, we might put the name of that catalyst or enzyme right there in order to make this thing happen, okay? But you have the before and after, all right? Now, we can also put in these little parentheses, like a parentheses S. Technically, it would go down here, but I didn't leave room for it. Sorry. And parentheses L, little l. All right. And here, parentheses AQ, and here, G. Okay. Now, what do those stand for? Well, some of those are pretty obvious. We had a piece of solid sodium. We had water, which is a liquid. All right. And we had the hydrogen given off as a gas. Okay. But some of them, well, we had that purple liquid left in the bowl. That would be the sodium hydroxide. But sodium hydroxide is not a liquid. It is a solid. We had little crystals. I think I showed those to you last time before I dissolved some in water to do the pennies last time. Anyhow, it is not a liquid. It is a solid that's dissolved in. We've made a solution. It's the solute in a solution. And so AQ means aqueous, which just means in water. Okay, basically. In other words, it's been dissolved in water. Okay, as opposed to water, which is just a liquid. Period. It's always a liquid, no matter what. Okay, and of course it can't be in water because it's always in water. I mean, I guess you could argue it is dissolved in water. It's yeah. Anyway, it can't be dissolved in itself. So anyhow, so it's a liquid. If something is just a liquid, like say rubbing alcohol, for example, is a liquid, then we'd put L after it. However, like the rubbing alcohol that you get in your container at the store, it's really actually a solution. So it's really, but it is a liquid itself, so we would put L. Okay, if it's a liquid itself, great. If it's dissolved in water or some other liquid, then we call aqueous. Okay, or particularly water. All right. Now, you notice there are also some numbers, little numbers here. Tell us if there's more than one atom of a certain element, then we'll have a little number here at the bottom telling us how many. So there's two hydrogens, but there's one oxygen, one sodium, one oxygen here, one hydrogen here joined together. And here we have two hydrogens stuck to each other. Okay, those are called subscripts, sub because they're below the surface. Okay, they're lower. All right, but problem is we have done some magic here. We have one sodium atom here. We have one sodium afterwards, right? All right, we have two hydrogens here, and we have two hydrogens here, but we have one here. So on this side, we have a total of 3. We have an extra hydrogen. Where did it come from? Did we steal it from somewhere else? Okay. Law of conservation of mass says matter or mass cannot be created or destroyed. So that says whatever we had before the reaction, we have to have the same thing after. So if we had 3 hydrogens afterwards, we have to have 3 hydrogens at the end. We can't just have, oh, we had 2 and we just made another one somehow, just poofed out of nowhere. Okay, so we have to do what's called balancing. Now, I'm sure everybody likes to balance. So we're going to balance this one, but we're not going to have any real hard balancing problems, but we will have some where you do some basic balancing. All right, so let's just do this. All right, the elements, we have sodium, hydrogen, and oxygen on both sides. Obviously, if we had one element but only on one side, that wouldn't be good either because that element can't just disappear. That element can't just go away. Or one just pop up out of nowhere, just like the hydrogen atom couldn't. So we should have the same elements on both sides. Okay, if we look on this side, sodium has 1, hydrogen has 2, and oxygen has 1. That's right. On this side, we have 1 sodium. That's good. Same as over here. We have 1 oxygen. That's good. But over here, unfortunately, we have 3 hydrogens. That doesn't work according to the law of the conservation of mass. Says you can't do that and come out even. It's got to come out even. Okay, you can't just have some random ones that pop in or pop out. All right. So some says, well, we could just put a 2 right here, and that would make 4 of those. Okay. The problem is, remember, compounds have a definite ratio. Sodium hydroxide is 1 sodium to 1 oxygen to 1 hydrogen. If you put 2 hydrogens there, it wouldn't be sodium hydroxide anymore. It'd be something different. Okay, it would have different properties. And so you've made it into a new compound. They can't do that. Okay, just like we can't just put a 2 over here on the oxygen because that would not be water anymore. That would be H2O2, which is hydrogen peroxide, and by itself can be very deadly. Okay, all right. So we can't just stick new subscripts on there to make it balance. To balance it, we have to do whole chunks. We either got to change the sodium. We have to change the whole number of water molecules, the number of sodium hydroxide molecules, or hydrogen molecules. Okay, and we can't change the formulas of those because those compounds have a particular formula. So what we do in this case, then we could put a big number in front of it. Okay. Now this is kind of like in math. If we had parentheses around this compound, that means 2 times everything in front of it. Okay. So you have 1 sodium, but now you have 2 times that sodium, so that gives you 2 sodiums. All right. Now that means 2 times the oxygen. There's only 1 oxygen there, so 1 times 2 is 2, and 2 times 1 hydrogen gives you 2. Okay. But we have 2 more hydrogens over here, so it's actually 2 plus 2, which gives us a total of 4. Okay. All right. Now the good news is we had 3 before. 3 and 2 are kind of hard to get together, right? Now we have an even number over there, so maybe we can make this number even. Well, if we put a big 2 right here, that means 2 times the water molecule. So 2 times 2 gives us 4, and 1 oxygen times 2 gives us 2. Okay, which means we have the same number of hydrogens, 4 on both sides, the oxygens 2 on both sides, but not the sodium. Now, notice I left sodium for last because it's just one element. So all I got to do is put a little 2 right here, and that means 2 times the sodium, so now we have 2 atoms. So in order for this reaction to work, it's going to use 2 molecules of sodium for every 2 molecules of water. And it will give you 2 molecules of sodium hydroxide and 1 molecule of H2. Okay, now it is balanced. We have the same amount of elements on both sides, and that is what conservation of mass tells us. Okay, so you need to make sure that you can kind of balance these equations. That's how you do it. You can only do it by putting a number in front of each of the molecules, and that means that number times everything that's in that molecule that's in front of it. All right. All right. Like I said, we're not going to give you some really hard ones, but we will have a little bit of that on the quiz, okay? All right, now, when reactions take place, they can be very fast or very slow. If you remember sodium, we said it's kind of basically rusting in water, basically, when you put it in there. But because it's such a strong metal, it rusts very quickly. Okay, a piece of iron, on the other hand, it also rusts. It also gives off heat, but nowhere near like the sodium does. And so it's a very relatively slow reaction, okay? So why are some reactions slow, some are fast? All right, why do they have different reaction rates? Okay, the rate is how fast they happen. Why do they happen differently? Okay, well, it just depends on the reaction, of course, but let's look at some of those reasons. All right, so just in order to have, so we have two reactants. In this case, we have two nitrogen atoms fused together and two oxygen atoms fused together. And they are going to, in order for them to react, first of all, they got to get close enough. Okay, they got to get close enough that they can either attract, repel each other, or do something to react and come together. Now, they also have certain parts of the molecule that need to come in touch with each other. Okay, they're not going to join just anywhere. There's only certain places on this. They're going to react with certain places on this one. All right. If they don't hit in the right place, no reaction. So they have to come together, have to hit on the right place, and then hopefully they will join together and end up with what we call nitrogen monoxide. One nitrogen, and mono means one oxygen. So one nitrogen, one oxygen, and they form this new product. That's what we would like to happen. But several things have to be in order to do that. They have to hit on the right parts of each other. They have to hit hard enough or with enough energy to make a reaction or a change happen. Okay, and they have to hit the right spot with enough energy at the right part of themselves. Okay, so I think I said that. Repeated it several times there. Let's try this again. So let's look at this. So what are some things that affect with it? Okay, first of all, they have to come together. If they don't react, if they don't hit each other, they've got to be close enough there. And now, if you have just two oxygen atoms in a whole room floating around with all these other atoms, the odds are they may never hit each other. First of all, I mean, they're not going to hit very often. So we can increase that by putting more oxygen atoms. The more oxygen atoms and the more nitrogen atoms have, then the more likely they are to run into each other. Okay, and so one thing we can do is increase the concentration of the reactants. The more reactants you have, the more they're going to react with each other. Okay, and the same thing applies within a reaction. When a reaction happens, we'll do some here in a minute, they usually happen really fast at first. Why? Because you have all these reactants put together, and they've all. It's kind of like going to a dance where all the boys and all the girls don't have dates. No one has a date. They're just there, so they're all available. All right, but as the dance goes on, people start picking partners, and there's less and less partners available. And so the reactions go very quick at first, or the dating goes finding a date goes very fast at first, but then as it gets on and there's just fewer people that haven't found a date, it's harder for them to run into each other because they got to move around all these other people on the dance floor that do have dates. And so it takes a lot longer for them to get it together. Okay? Well, the same thing happens in a reaction. When you first mix chemicals together, you have the two reactants. Well, they can react with any of the other ones that are next to them, or the other chemicals, the other molecules, boom, boom, boom. So they react really fast. But as it gets longer and longer, you have these few that are still not matched up. They have to go search for someone to match up with. Like here's this one over here and this one over here, but if they don't run into each other, so all reactions start fast and then they kind of taper off as all the reactions get used up. Okay, but if we can keep that concentration high, we keep adding more reactants to it, then it will keep going faster. So the higher the concentration, the faster the reaction rate. The lower the concentration, you're going to have a low reaction rate. Okay. Another thing is temperature. Okay. What do we know about temperature? We know if you have temperature, they will move faster. That's right. They're going to move faster. Therefore, they're more likely to hit with enough energy to make the reaction happen. Okay. And if they don't, they hit off this one, bounce off another one. The faster they're moving, the more likely it's that much quicker they'll bump into another one, and maybe eventually they'll run into one that's turned the right direction, and they will join together and make a compound. Okay, so the faster they're moving, the more things they'll bump into, and the better the odds are that they will react. So in general, we say if you increase the temperature, you increase the reaction rate because you're increasing how fast they move, therefore they run into each other more often and quicker, and they also have more energy, so they're more likely to react when they do line up with each other. All right, so temperature tends to do it. Okay, going back to this nitrogen oxygen thing we're talking about, they have to have a lot of energy. In fact, the only place this really happens most
Nitrogen is something plants need, but they can't use this nitrogen. These two nitrogen atoms that are just floating around by themselves. Plants can't take that out of the air and tear them apart and use them, okay? Because they hold together so strongly. Remember, they're nonpolar covalent. They share those electrons, and they like each other, and they're no positive or negatives. They don't like to react with other things. They don't like to come apart. But in order to get them to come apart and join and make nitrogen and oxygen, which then can be changed into something that plants can use, it takes a lot of energy. And usually that energy comes from lightning. And lightning strikes tend to, as it goes through the air, all the nitrogen and oxygens nearby have enough energy that they begin to react with each other. And now you have all this NO, nitrogen monoxide, in the air that rain can pick up, bring it down into the ground, and then it can be changed into forms like nitrate. Ammonium nitrate is a very common fertilizer that plants can use to take up. Okay, so anyhow, so if you have a higher temperature, they're moving faster, they have more energy, and they're more likely to have enough energy to react. Something extreme ones like the nitrogen oxygen, though, take lots of energy, like a lightning bolt. Okay, all right. Now, so we have these reactions. We want them to happen, but we don't want some reactions to happen all the time. Okay, so for example, let's just go back to here real quick. And let's say I have papers. I have lots of papers on my desk, okay? It's not even my desk, but it still has a bunch of papers on it. See, there's papers over there. Okay, now, what happens to paper when exposed to heat? It catches on fire, okay? What if paper just, like that sodium, when you just put it in water, did I have to do anything to it? No, it just it reacted and started building up heat and then exploded. What if paper did the same thing? All right, in other words, what if somehow some of these atoms got enough energy they just burst into flames? That would be bad. Okay, my desk would just, everybody's desk would just all burn up. Of course, then you would have an excuse to not have your homework, I guess. So there's good things about everything, but that's not where we're going to go with this. Okay, in order for this reaction to happen, we have to add some energy. Paper is not just going to spontaneously burst into flames. What was the Ray Bradbury book, 415 degrees Fahrenheit, something like that is the, or 451. Anyway, whatever. I should have studied up on my Ray Bradbury before I did this. But anyhow, you have to burn paper, you have to get to a certain temperature. Okay? Now, once you start burning the paper, does it need any help to keep going? No, it will just keep right on burning. But you got to give it that little thing. Otherwise, things would burst into flames all over my desk, and that would be a bad thing, at least for me. Now, the energy it takes to make the reaction happen, okay? Some things are what we call spontaneous reactions. That's like the sodium in the water. As soon as those chemicals mix, boom, there's going to be a reaction. It doesn't matter, okay? It doesn't need anything to trigger it. You can put oxygen and hydrogen together, and they can just mix and be gases. But if you get a spark of energy, then they will blow up and produce water vapor, H2O, okay? But they will do that because of the energy. But it takes the energy to set it off. A piece of paper takes a certain amount of energy. That is called the energy barrier. Why? Because it keeps these reactions from happening. So basically, it requires, we got to break, these chemicals in here are already bound together. We need some energy to break them loose. All right, and then it will continue on its own, but you got to have something. So if we take our match right here and we burn the paper, all right, it is breaking bonds in there, okay? And it took this energy to get it started. Now, once it gets going, it takes less energy to hold the smoke that's coming off and the ashes that are flittering off all over my desk, making a mess here, okay? It is difficult. It doesn't take as much energy, and so it's also giving off a bunch of energy because it doesn't need as much anymore. All right, let me go to this real quick. All right, we'll put that in the sink where it can burn itself out. Nice smell of burned paper. You can't smell it. Sorry, that's the disadvantage of not being here in person. Okay, all right, but. When I light the match, I'm overcoming that energy barrier that allows the reaction to take place. And in the case of paper, Once it takes place, it just keeps going. Okay, and we'll talk about why here in a little bit. All right, so that is called the energy barrier. That's what keeps these reactions. Most reactions don't happen just spontaneously like the sodium and water do. Something has to give them enough energy to get them over the energy barrier. And the energy that gets you over the energy barrier to make the reaction take place is called the activation energy, because it's the energy that will make the reaction become active. And now you've got burning paper, right? Which is much more exciting and active than just a boring plain sheet of paper, especially if it's just got science notes on it, right? All right, so let's go back and talk about that for a little bit. Now, how do we control, how does nature control these reactions? How do we control it in our bodies, for example? Well, let's look at some examples again. All right. So first of all, here's the amount of energy that's involved in these nitrogen and oxygen molecules holding them together. In order for them to react with each other, there's this energy barrier, this distance from here to here. Okay. And it's going to take that much energy, activation energy, to get it over that and cause this reaction to happen. So you're going to have to add this much energy. All right. Now, notice over here, the energy level of these molecules is still higher than it was over here. It takes more energy to hold one nitrogen and one oxygen together than it does for two nitrogens to hold each other or two oxygens to hold on to each other. Okay, so we start with a fairly low energy. We add lightning bolt, whatever, some kind of strong energy that allows them to react with each other. And once they have reacted with each other, they use up more energy than they did before. Okay, unlike the paper, which after it reacts is giving off more energy, and it takes less energy to hold them together afterwards. Okay, all right, but we'll get back to more of that in a minute. But let's talk about this right now. This is the barrier, right? This is the amount of energy it takes to make the reaction happen. What if we could reduce this amount? Okay, where it wasn't so hard to get it to happen. Okay. Here's another example. This is ozone, which is just 3 oxygens stuck together, by the way. We breathe oxygen with 2 oxygens. Okay, ozone can be broken down into O2, okay, or 2 oxygen atoms, okay? But there's an energy barrier, all right? And so it doesn't happen very much except for up in the higher levels of the atmosphere. But it turns out that if chlorine, notice chlorine, the Cl is written over the little arrow here, it's like an enzyme or a catalyst, all right? And what it does is it says, hey, you don't need this much energy when I'm around, you only need this much energy to make it happen. And makes it a lot easier for it to happen. Okay, so it lowers that energy and makes it more, that's one thing catalysts or enzymes do, is that they make it take less energy. So say if I put a chemical like the potassium nitrate we did on the paper the other day, okay, if I paint that chemical on it, now it doesn't take as much heat to keep the paper burning. Instead of using a flame like the match, I can use the punk, and just the glowing embers will be enough to catch it on fire, and then it will spread and keep burning everywhere that the potassium nitrate is present. Okay, so it's kind of the same thing here. It is lowering the amount of energy it takes, so it makes it a lot easier for the reaction to happen. So catalysts can speed things up by lowering the energy. Now, interestingly enough, just tie this into ozone. The ozone layer has a bunch of ozone in it. Normally there's a high energy level here to make it break down into O2. But we have what we call chlorinated fluorocarbons, CFCs, okay? And basically they have all these carbons on them. Well, or excuse me, chlorines on them, okay? Cl chlorine on the carbon. It's just one carbon with 3 chlorines and a fluorine. Well, it turns out there's another one, CFC12, which has 2 chlorines. Anyhow, if the chlorines from these are present, they can cause this reaction happen, and then you get a bunch of, and these chemicals are found in a lot of the aerosols that we used to have and so forth, and when they get sprayed in the atmosphere, if they move up into the atmosphere, they can cause the ozone to break down. And there are, we've heard, the hole in the ozone. Since they have made it illegal to produce many of these, we have seen the ozone begin to fill in some of those holes, okay, whether they completely go away or not, but at least it seems to be helping that the fact they don't use these CFCs or chlorinated fluorocarbons nearly as much as they used to. The Freon that was in air conditioners and refrigerators and things like that used to have these in it. Now they use different ones, okay? Because the chlorine acted as a catalyst to destroy the ozone layer. All right. So a catalyst is something that helps speed up the reaction, and one of the ways it can do that is by lowering that energy it takes to make it happen. All right. Now, if it happens in non-living things like a lab or something like that, we would call that a catalyst. All right. So this second, we'll do an example of a catalyst. All right. Here we are. You can't see me very good. That's okay. You probably see me enough more than you want to anyhow. All right. We're going to start here with hydrogen peroxide. Okay. Hydrogen peroxide is a chemical everybody should be fairly familiar with. Some people put it on cuts and it bubbles. Some people put it gargle with it or use it for mouthwash, whatever. Okay, and it's a clear liquid. Its formula is H2O2. Okay, just like water, but with an extra oxygen. And if you leave it here, now just for the record, it's a very poisonous substance, but this is only a dangerous substance, but this is only 3%, so it means it's 97% water. So really, it's. I'm not saying you should swallow it and everything, but it can be used like people have used it for on cuts and mouthwash and stuff like that with no bad harm effects. Okay. Now, over time, if you were to leave this bottle and leave the lid off, it would go flat basically because over time the H2O2 would start giving off oxygens. And before long, it would be down to 2%, maybe even 1%, and eventually it might even just be a jug of water, okay? So it's very important. Your mom may yell at you if you leave the lid off, because when you're a kid anyhow, because it goes flat. Well, what happens in case the oxygen is freed off and the water molecules are left behind, and you just have a bunch of water, which doesn't do much good, okay? So it happens very slowly, though, over time, because just at room temperature, there's nothing to encourage it really. But if we add a little bit of this is a black powder. This is called manganese dioxide. Guess what? Manganese is the first element, and dioxide means there's 2 oxygen atoms. All right, if I put some of this in there, all right, if you look closely, I think you can see it. I don't know, I'll bring it up a little closer. You can see bubbles at the top, okay? So that top stuff there, bubbles, 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 okay? It's bubbling at the top, okay? You can see down the bottom that cloudiness. Some of that's the black stuff, but also it's little tiny bubbles coming up, okay? So it's starting to bubble a lot, all right? So what have we done? We've added a catalyst, all right? Manganese dioxide is a lab chemical, all right, that I've got. You feel the sides hot, okay, which otherwise, if you just let it do it on its own, it would never get hot. It speeds up the reaction. It lowers the activation energy. It doesn't take as much energy now for it to break loose and give off those oxygens, so it starts bubbling off. Okay. Now this happens when you put it on a cut too, but instead of a catalyst or a chemical that we've added in the laboratory, okay, you are actually adding enzymes. Enzymes are pretty much the same as catalysts, except for that they are in living things like you. And so your cells have enzymes in them, and those enzymes cause the hydrogen peroxide to give off oxygen bubbles, and that oxygen kills bacteria that cause gangrene and stuff. They live under your skin where there's no oxygen. They don't like oxygen, and the bubbles of oxygen kill them. Okay? Now, that's not necessarily the best way. I think they still recommend you put antibiotic ointment or methylate, something like that on it instead, but because it can also do damage to good cells, but since it's only 3%, it is a way to kill the bacteria. Okay, so we have added a catalyst to do that. Now, if I wanted to use some living tissue, then I could have an enzyme. So we take this slimy looking stuff, which is chicken liver. Okay, it is living tissue. So instead of catalyst, it would technically be an enzyme because it has enzymes in it. All right, so your liver has quite a few enzymes because it does lots of little things for you. Everybody needs a good liver. So you shouldn't drink alcohol so much because you can destroy your liver. It filters out poisons, it stores chemicals for you, does a lot of good stuff for you. All right, now, if we take that liver that's in there, and we're going to add some hydrogen peroxide to it, and see what happens. Try to add roughly the same amount. Okay, so we get the hydrogen peroxide and we add it to the liver. Let's see what happens here, if it bubbles or not. And yes, once again, it bubbles. You can even hear it fizzing. I don't know if you can hear it, but it's actually fizzing in there. All right. So it also has a lot of chemicals, just like your skin would. If you got a cut on it, it would open up chemicals from your body that are going to react. Okay, and they speed up the reaction and make it bubble quicker. And that's why you get all the bubble on your cut that hopefully kill the bad bacteria. All right, we're going to do one last one though here. And let's say this time we have hydrogen peroxide again. Okay. All right, so we've got hydrogen peroxide again. But this time we have a piece of liver, but this liver has been cooked. Okay? So they cooked your goose well, they cooked their liver, all right? So we're going to take this liver. All right, because it's been cooked. Frankly, I don't like eating chicken liver, but it's okay. But the best thing to do with chicken liver is try to catch a catfish with it or something. But, that's just my personal opinion. Now, if I put this bull piece of liver in, we will notice that what happens? Basically nothing. Okay, for the most part, nothing. Very little. There's a few bubbles coming up off of it, but very little. Okay, a little bit faster than just plain hydrogen peroxide sitting by itself, maybe, but for the most part, not much. Why? Well, because enzymes are different than catalysts. Catalysts are fairly simple compounds. For example, this manganese dioxide is MnO2. One atom of magnesium, two atoms of oxygen. That's it. Enzymes are very complicated compounds called proteins, which we'll talk more about in chapters 22 and 23. But they're long chains. They're very long and complicated, and they are usually fairly specific to certain kind of reactions they work on, especially in your body. Your body doesn't want enzymes to just go around making all reactions happen all over the place. They want, let's make this enzyme so it'll make this thing happen, or it'll make this enzyme so something else happens. Okay? It wants very specific ones. All right? And so they're very living things, much more complex, usually proteins, and they are usually very specific, so that you don't just have all these random reactions going on inside your body at all times. All right? On the other hand, catalysts tend to be in non-living things. They tend to be much more simpler, and therefore, because they're simpler, they're very non-specific. They kind of may cause lots of different kind of catalysts or enzyme reactions to go on. Okay? All right. So that's kind of the difference between those two. All right. Now, let's talk about exo and endothermic reactions and entropy, and then we'll be pretty much done. All right. Sorry, not as many demonstrations this time. That's the way it works sometimes, just burning some stuff and a little bit of bubbles. All right. So let's talk about endo and exothermic. All right. Do that. Let's go look at some pictures over here. I think I have some that will show that better. All right. So here we have hydrogen and oxygen. All right. And it takes a certain amount of energy, pretty high energy level, to hold those two things, the hydrogens and oxygens, together. We have to add energy to make them react and then blow up. If you were here last semester, we did a sound thing where we did the sonic boom, and basically it was hydrogen gas, oxygen gas. They blew up, and if you looked inside the bottle at the end of it, you would see a bunch of vapor, water vapor on the side that was formed by it. And that's basically what we did. Okay, but to do that, we have to add energy here. We have to light it and add heat energy. Okay, now it heats it. Now it reacts. Once it gets started reacting, but notice this is different. Water takes a lot less energy to hold together than it did to hold together the hydrogen and oxygen levels. Okay, so it takes less energy. So what's going to happen? You had this much energy. You added some energy to get up to here, and now the water only needs this much energy to hold itself together. Well, that's where the explosion came from. That's where the light and the sound and the heat that was produced when you blew it up. Why? Because that's extra energy that's being released. And so your products need less energy to be held together than your original reactants. And so you have an excess of energy that's given off. All this difference between where you started and where you ended up is the extra energy that's given off. And so we say this is an exothermic reaction. There's a net release of energy. Okay. Now, here's the energy they had. Here's the energy you absorbed. You subtract how much is given off, and that tells you what their the net energy of the reaction is. Okay. Now notice it needs less energy now. That's why that's a negative number, but that means it gave off extra energy. Okay. And so it is an exo. Exo means to give off or exit. Energy exits from the reaction. Okay. When we burn the piece of paper, there's energy exiting it. Okay. Because it didn't take as much energy to hold the soot and the ashes and the smoke together that it did the paper, holding the paper together. All right. So that is an exothermic reaction. Notice it still has to take energy to make it happen. But since the products don't need as much energy, it releases energy. All right. Now, on the other hand, if we have the nitrogen and oxygen molecules, and we have to have a lightning strike to give all this energy to make them react with each other, once you get this nitrogen monoxide, it still requires more energy to hold them together than it did to hold these together. So most of the energy stays right here in these molecules. All right. So we call this an endothermic reaction because it took all this extra energy just to get them to hold it together, So instead of releasing energy, it is actually, you have to put energy in. Now, question is, which of these are going to occur more readily in nature or more likely to just keep going on their own? Well, it's the exothermic. Since they're giving off energy, the energy they're giving off, as some of us say the paper burns, is enough energy to get some more of the paper to jump over the energy barrier, and it just keeps on going and keeps on going. So exothermic or more, they're more likely just to continue to happen in nature. Endothermic, you have to keep adding energy. You got to get a lightning bolt. Well, if you want any more of this to happen, you're going to have to add some more lightning bolt. Okay, this would be like if I lighted the piece of paper and as soon as I took the flame away, it went out because it didn't have enough energy. I'd have to keep feeding energy into it. Endothermic will require you to constantly be adding energy in order to keep it going. Okay, and that's what endothermic is. Okay, now let's talk about this in terms of entropy. All right, entropy is a word you may have heard before, E-N-T-R-O-P-Y, entropy. And basically, entropy has to do with how organized and complicated things are, okay? When energy is used to build more complicated structures, okay? Sorry, I said I'm gonna bug me, but it did. Okay, when we use build, okay, so in nature, or I should say in the physical world, the most common thing is for entropy to increase. And we say entropy is disorganized, disorderly. Okay, after I burned that piece of paper, instead of one nice little organized piece of paper, now I have smoke that's scattered out all over here, and I got ashes that are scattered over there, and I got heat that's just spreading out throughout the room. Just spreading out, it's becoming more spread out, less organized. Okay, and so that's entropy. We have increased the entropy, okay? And in generally, we say exothermic reactions are going to increase the entropy because since they're giving off energy, it continues the reaction to go on. This energy tends to spread out, usually as heat, other things, sound and otherwise as well, but motion. But eventually it's going to get spread out, and it's so spread out, it's like, well, the temperature in this room didn't go up from all that heat, even though it produced a fair amount of heat, but it just got spread out, and now it's not there anymore. And all those chemicals are no longer held together in a piece of paper. They're less organized. And so we say that the entropy has increased because that's what entropy is. All right. Now, living things that are still alive are constantly taking things and using up energy. That's why we have to eat food and sugar and all that kind of stuff. All that stuff, that fuel, we use it to put things back together. We decrease entropy. We organize it back into our body parts and things like that. Plants organize carbon dioxide and water and things into trees and grass and all those other things out there. Okay, so living things are constantly using energy, endothermic, putting in energy to make reactions, to build things and make things more complicated. Okay, so endothermic reactions require energy to keep going, and they tend to decrease entropy. All right. And that's what living things are constantly doing. All right. Then, so as long as I'm alive, my body is constantly building, putting things together, doing all these endothermic reactions, trying to build it together, make me a more organized, basically. But as soon as I die, I start breaking down, okay, because my body is no longer doing those reactions and trying to hold things together. And that's why we say entropy is natural. That's just the natural tendency is for things to fall apart. Okay, it's kind of like my daughter's bedroom. I have two daughters. One, we keep working hard to keep her room organized and orderly. Okay, and that's what endothermic reactions are. You got to work to keep it. The other, yeah, just kind of let it go. Well, before long, it was all disorganized. You can't find things. There's clothes all over the place. You may not be able to find the clothes you need, or this, that, or whatever. Okay, and that is exothermic, and that is decreasing the entropy or disorganizedness. And that's what happens to our body as soon as we die. Okay, it starts breaking down because that's just the tendency of things to become disorganized. The energy becomes more spread out and less organized, and that's what entropy is. All right. But as living organisms, we're constantly fighting against that because we're trying to organize using energy to build things that are more complicated and more organized, like our bodies and other structures, and we're constantly fighting that. All right. One last thing, talking about enzyme and catalyst. One of the characteristics of the enzyme is this. For example, if you look in here, you still see the manganese dioxide. Okay, it's quit bubbling. All right, it's bubbled out all the oxygen is. But if I pour some more hydrogen peroxide in, guess what? It will start bubbling again. Why? Because the manganese dioxide is still there, and it will still attack, and it will start breaking down the hydrogen peroxide again. Why? Because enzymes do not take part, and catalysts do not take part in the reaction that they stimulate. Okay, they cause it to happen, they make it happen, but they're not affected. It's kind of like that person in school who every time they're around, they start fights, but they never end the fight. Okay, but when they're around, they can make so and Sarah mad at Joan and whatever, and they get in a fight. They start it, and then they step back and watch them fight. Okay, well that's kind of what enzymes do. They get the reaction started, but they don't get used up in it, so they're still there. Okay, now the other thing about enzymes, I'm sorry, I said this is all, but I forgot this. The enzyme, how do enzymes work then? Well, one, we said they could lower the activation energy, but and catalysts do the same. But enzymes are a particular shape. That's one reason they're so complicated. They have to be a certain shape. And they are a shape where these two chemicals, the two reactants, the chemicals you want to react together will fit in there just right. And they'll fit in there just right so that the two parts that need to hit each other. Remember we said they have to hit at the right sites where they want, the active sites where they want to react with each other. Well, when they fit into the enzyme, they're facing each other, right next to each other, and those active sites, the reaction sites, are right next to each other. And boom, so it helps the reaction. They're kind of like a matchmaker. They bring these two reactants together and try to make conditions just right for them to react and join together. Kind of like matchmakers. Now, just for the record, in your body, there are also enzymes that break them apart. Okay, because sometimes your body puts things together, sometimes it needs to take them apart. So they're more like divorce lawyers. They bring those two together, break them loose, and spit them back out. Okay, so it can work both directions. They can either be matchmakers or they can be divorce lawyers. Whatever, your choice. Okay. All right. Well, anyhow, that's it for this. Hopefully, you have taken your chapter or exam number 1 on the first 4 chapters. And if you haven't, I think you have till midnight tonight. But then you have your questions for chapter 20 by next Monday, or by Saturday, sorry. And then next week you'll have your quiz on chapter 20. All right. Have a great week.